Good afternoon, everyone. I will discuss. I'm very pleased to have the opportunity to discuss here about the future of climate projections with a standpoint of the global models this time. And I don't think there is a consensus here. We just get out of a big exercise, which is CMIP 6, Climate Model Intercomparison Project, phase 6. So the consensus is still building on, and I think this is much a view which is biased towards IPSL, Institut Simon Laplace in Paris in a way. So as I said, we came out to CMIP 6. I think it's been a long and tiring process, but also a big success. We had many improvements in the model protocol with better external forcing terms, new scenarios, the shared socioeconomic pathways, a climate data request, which has led to normalized outputs, also a very efficient distribution system, which is called the ESGF, which the climate data store builds on. We also have an erratum service. So that's all for the technical side of CMIP. But on the model side, I mean, we also have models with improved physics and also higher resolution. And as a result, these models also simulate better the observed climatologies. And we have a huge database for the coming 10 years with a large multi-model ensemble, but also initial condition ensembles for each model, which Cordex can build on. So as I said, there have been some improvement in a number of climate metrics. Here I show patterns of SST, reflected radiation, outgoing long-wave radiation in these models. The CMIP 5 models are in green, the CMIP 6 models, or at least the first ones, are in black. And you can see for a metric like the IMSC, the trend is really going towards lower IMSC, so the models are becoming better. That's the case in general, that's the case for the IPSL model. But it's true that we've spent a lot of effort in tuning these models, in making, in changing some uncertain parameters to try and match better the observation. So it's no surprise that these metrics are improving over time. But still, there are other metrics like precipitation for which we don't really have parameters to tune. I mean, they're more like an emerging property of the model. There's still some improvement as well, especially in regions which have shown persistent model biases. I mean, regions where the precipitation is difficult to simulate, like the Amazon, which is often too dry in models, or the Pacific, where there is what we call a double ITCZ. In the models. So there is also an improvement for these metrics. Yet, if you look at this new generation of global climate models, the CMIP 6 models, there is still a relatively wide range of climate sensitivity, which we can measure with the effective equilibrium climate sensitivity, ECS, and that range goes from a bit more than 2 Kelvin to a bit less than 6 Kelvin for a doubling of CO2 at equilibrium, or the TCR, the transient climate response, the warming at the time of CO2. If you increase CO2 by 1% per year, then the range is between 1.5 and 3. So there's still a big challenge ahead of us to decrease and constrain better this range, because this is a key thing that's going to determine the future climate. If you look at multiple lines of evidence, like Steve Sherwood did in a big review paper, looking at process-based evidences, or looking at the historical record, or looking at paleoclimate evidence, then you can narrow down a little bit that range. But the distribution is a bit more skewed. That's the black line, and you can't really exclude large ECS like 4 or 5 Kelvin warming for doubling CO2. So there's still a key issue here that we need to continue to tackle. Another finding in some models is the importance of low frequency internal climate variability. Some models don't have much, some models have a lot more, and we don't really know where the truth is. Most of it, originates in variation in the North Atlantic with the AMOC, the Atlantic Meridional Overturning Circulation, which shows some variations on a sort of like a 200 period in our model, but in some other models as well. As I said, it depends a little bit on the strength of that depends a little bit on the model. In our model, at least, there is a significant correlation between the AMOC trend on the trend in global surface air temperature. So when there is when the AMOC is increasing, then the global mean surface temperature is increasing, and it has important consequences for the climate in some regions like Europe. So we have performed a big ensemble with different initial conditions. And the members with the weakest warming and also the best match to the observed patterns of SST change are also the members with the strongest weakening of the AMOC over the second half of the century. And there are some evidences that AMOC is decreasing. Of course, it's hard to observe AMOC, but there is some evidence that some members are more realistic than others. So that has, I think, important implications on the choice of the members when you do downscaling in an exercise like Cordex. Just to illustrate that a bit more, here is again the AMOC over the historical period and into the future. If you look at the multi-member mean from a given model, then you get what we call the forced response. So that's the response to external forcing. That's the red curve on this graph. So it's pretty stable, and then it starts to decrease because of climate change from year 2000. But if we look at these members that we think are more in phase with the observations, that's the blue subset, then you see that the AMOC increased and then started to increase much earlier than in the ensemble mean. And conversely, in the future, it keeps decreasing, but maybe a bit less than the ensemble mean. So there is clearly some historical members are more realistic than others in terms of how their internal climate variability is phased with respect to observations. And I think this should raise a paradigm shift in how to do downscaling, whether it's dynamical downscaling or statistical downscaling. If you take an example here, just in a sort of a pure perfect model word, we take two ensemble members, number 29 and number 25. They have the same phase of the AMOC, so they're sort of consistent with each other in terms of their low frequency internal variability. And if you try to do a bias correction of one with respect to the other, just as an exercise, then you get the same answer in terms of this Europe summertime temperature, both over the historical period and into the future. If you instead, you try to bias correct one member with respect to another member which has an opposite phase in this AMOC low frequency variability, then you get an offset because the two members just are just a difference in the historical period, and that offset is there until the future projections where it shouldn't be. So I think the next question is whether this has implications beyond the mean, but I think we need to rethink a little bit the choice of members when it comes to downscaling. A word on scenarios, maybe. So we have Ssp scenarios with a range of radiative perturbations from the lowest to the strongest radiative forcing in 2100. That's the number 1.9 to 8.5. And then different context for the socioeconomic pathways from SSP1 to SSP5 that corresponds to different story of the word, whether it's a global word, a regionalized word, a word that is geared to sustainable development or not, etc. There are questions coming now on how realistic are the SSP1 1.9 and SSP5 8.5 on both ends. 1.9 may be really low, sort of unrealistically low emission, 8.5 maybe unrealistically high emissions. So this is, I think, something to follow in the future. Maybe we need to refine some of these scenarios. I'm sure there will be more emphasis on overshoot scenarios where we go above 2 degrees and then we go below with carbon dioxide removal techniques. Either I would say it doesn't make much difference until 2050 for such scenarios. The difference is more in the second half of the century. Also, I would flag the importance of short-lived climate forces like ozone, like aerosols, which are clearly have an impact on the regional scale. I mean, they're short-lived, so they don't go very far from the source regions, and they have a regional climate impact. We do see evidence that that aerosols now may be decreasing not only in Europe and North America, but also in Asia. So there might be a decrease in the global mean as well. Another piece of work that we're doing, which may influence the way we do climate projections in the future, is to have a much more holistic vision of bias correction. So we've been quite used, at least in global models, also regional models, to the nudging method. So basically, we have a relaxation term towards reanalysis. So we force the model to be relatively close to observations, to meteorological reanalysis. That's this x minus xr term with a time scale tau. What we started to do is to see this term as basically a model error. So we need to nudge the model because the model has well, there is a stochastic component in the climate system, but also the model has some errors. On this term, if we average it over time, x minus xr average over a long enough period, which is the g term below, then it can be seen as an error correction term. So it's a small term, but we add it to the model, to the free-running model every time step. And that way we can do what we call a non-line bias correction in the climate model, but still it's a free-running model. So we can have a more comprehensive approach to bias correction with correcting biases in SST and sea ice cover when it comes to atmospheric model, but also correcting the dynamics. Typically we apply this correction term on the wind term, U on V, and also temperature. And then you can still do offline bias correction, but maybe the need is less if you do this online bias correction first. We have preliminary results that show that it basically works. I put the names of the colleagues involved at the bottom of the slide. So on the left, you have a completely free-running historical climate simulations here, which you can compare to ECMWF reanalysis in the middle, so you can see some biases. This is surface pressure here, the climatology of surface pressure. You can see some biases in the Southern Ocean, also in the North Atlantic Ocean, and other places. And then the simulation on the right has this small correction term, which is applied every time step, and you see that you're able to correct a number of these biases in the mean. So now the question is, does it make also a better model for some other metrics? We think it might. So what's next? Clearly, there is a trend towards higher resolution, both in the atmosphere and in the ocean. However, there's still a question of how much and how fast we need to increase the resolution, and what for. It's not the perfect solution. We know that it's not going to solve every problem in climate models. We also know that we still need to sample structural and parametric uncertainties, and also to simulate a large number of years because we want to sample internal variability. So there is a question on here, and there might be different views on how important it is to increase resolution in the climate models, but clearly everyone is going into that direction, maybe at different speed. Clearly, I would say climate models are not the best models to look at climate extremes, but they're sort of reaching a point where we can start looking at them, and then we realize that there isn't a very good representation of extremes, and of course that's what we have: regional dynamical downscaling, statistical downscaling. But for something like heat waves, we do see a very clear signal in the climate models. This is an example for heat waves over France. There's a clear increase in these two indices, three consecutive days of maximum temperature on 3 consecutive days or 7 consecutive days, but we can't match the observations. The model doesn't manage to make climate extremes as extreme as in the observations. So the question here, why? And then there is a challenge on improving this, and it's even more difficult if we go to precipitation. So I think this audience has a very clear view of what is driving the model development for adaptation. So maybe I thought I would spend a bit more time on mitigation, the goals for mitigation, because this is also driving the global model development in the future. I mean, we still have a lot of work to do to understand and better constrain climate feedbacks, also through better physics, and of course cloud feedbacks are very important in that respect, but also surface atmosphere interactions, all sorts of Earth system feedbacks like permafrost, methane, aerosols, which are important. The quantification of uncertainties, as I said, is really a key subject, and we're sort of bringing new methods as well to do that. The global models, you can also do paleoclimate simulations, which are important to inform the future. So there is a challenge to relate better the past crisis to the future risks. This can be done for ice sheets and sea level rise, which is an important climate impact as well. We're working a lot on the carbon cycle. We're trying to couple the nitrogen and the carbon cycles, having better representations of forestry, crops, permafrost, fires, and the interaction with the rest of the carbon cycle. There is the whole issue of carbon dioxide removal and even carbon capture and usage, and all this business of negative emissions and how to simulate and assess the potential. As I mentioned earlier, overshoot scenarios, short-lived climate forces, geoengineering are also drivers for all this global climate modeling community. There is a framework for that. I mean, the World Climate Research Program, I think was mentioned in the first talk, has set up its strategy. It has come up with a number of lighthouse activities. One of them is the Digital Earth, which also Europe has adopted. So it's still, I think, a really relatively loose concept, but it's about having a more dynamic representations of the Earth system, completely digital, with a blend of models and observations, but it's not obvious how to best do that. So you can explore the past, the present, and the possible futures of the Earth system. There is still here some discussions about resolution, about how exactly you want to do that. Then WCRP also has a number of questions, is organized around a number of questions, which I think are useful to flag, with the regional climate, of course, being very important. I think for the sake of time, I should go to my conclusions. I would say clearly CMIP 6 has been a success. Codex will continue to complement such an exercise. I would argue that the role of internal variability should not be overlooked. I mean, it's important in some models. Then that raises some questions about how many members you want to then scale, which ones, how many you want to consider for impact studies, and so on. But that also raises the question of how to initialize global simulations. I mean, we just initialize them from control simulations. Maybe there is a better way. We should bridge maybe better with decadal predictions. On scenarios, the Ssp scenarios are a very good basis, but as I said, the very low and the very high scenarios are maybe questionable. Maybe they should be reconsidered in the coming years. Overshoot scenarios become more relevant, short-lived climate forces as well. There is a push towards higher resolution in climate models, but as I said, how much, what for? And that should not be at the expense of sampling structural and parametric uncertainties, sampling internal variability. I also repeat the importance of bias correction, and maybe there is a better way of doing it. I mean, there is no reason just to leave it for the end. Maybe we can have a more comprehensive approach. And also, we try to make more model development so as to bring more consistency in the model. So we go a little bit one step towards the impact. So we try to represent better the hydrology. We try to represent better agriculture, crops, etc. So we have more information available in the model before it goes to impact studies. So I think that's basically all I had to say. As I said, it's a strategy that is also under development among the global climate community, and there might be also different views on this. Thank you.